So, as we approach testing time.
Oh my god, no.
It's coming. Yeah, it's like next week. I want to do a little bit of reviewing with you guys. Plus, this is stuff that we've been talking about, so it is important to kind of know.
Let me close the door so I'm not screaming out in the hallway. Oh, it's too hot for that.
There we go. Close it up a little bit so I'm not screaming. Now, as we discussed in the past, uniform circular motion. Stop moving. This is probably something that's going to be of importance since it's something that's very much in the curriculum. It's something that you will want to know for the test.
Attention students and staff. We have abundance of lost keys. So if you're looking for your keys, please check the main office.
I lost a bunch of keys. Anything with a Mercedes logo on it, that one's mine. I lost it. No, but I will when they give me those keys. What is uniform circular motion? In your own words. It's something doing what? Going in a circle, right? Circular motion. It's just getting spun in a circle, right? So we talked about... No, I'm not going to say it because that's question number 3. What does uniform mean? What? Your clothes, you wear a uniform. What does it mean when you're wearing a uniform, though?
Look presentable.
You look presentable.
Not really.
What? Hopefully you're put together. But if you wear a uniform, what are you wearing?
Clothes.
Clothes. What kind of clothes?
Annoying, terrible, tight clothes.
Annoying, terrible clothes. Okay. I'm looking for something specific, though. Brad, as you come and tell me, what does uniform mean? If we're all wearing a uniform, what are we all wearing? Matching. It's the same, right? Uniform circular motion means the motion is the same the whole way through. So AJ, when you wear a uniform, you're wearing the same clothes as everybody else. Uniform just means the same. So uniform circular motion means it's not changing as it goes, right? Constant velocity, right? Maybe? No. Constant acceleration, constant force, constant something. We're going to talk about it in a second, see what you guys remember. Give me an example of uniform circular motion. Something that just keeps moving in a circle.
Air.
Air in a convection current. Uniform circular motion. BJ, give me something else. What?
Sea currents.
Sea currents, sure. BJ, give me something that moves in a circle. Uniform circular motion. Give me something that moves in uniform circular motion. Clock! Right? Second hand on a clock. Minute hand on a clock. Especially if it's a good clock, like a Rolex. Rolexes don't tick. Nice and steady. Alright, Brad. Now come to you. Redeem yourself, sir. Give me something that moves in uniform circular motion.
You hear me, Dad? He's smart. Signed up and his girlfriend and not us.
What? Just woke up? Okay, how'd you get here this morning? You walked? Did any cars go past you? How are their wheels moving? How would you describe the motion of their wheels? They go in a circle. It's uniform circular motion. Beautiful. See, I knew you knew the answer. Now you're right. So, when we look at uniform circular motion, we're looking at something moving in a steady circle. It means it's not going to change. The circle's not going to suddenly get bigger. Not going to suddenly get smaller. Right? It's not going to speed up, slow down. It's going to move at the same speed in a circle. A satellite orbiting a planet, a moon orbiting a planet orbiting the sun, somebody's spinning a bucket of water. Remember we did that experiment where we spun the bucket of water? Someone's spinning a top. Right. Me spinning around in a circle, assuming I never stop. All those things are uniform circular motion, theoretically. Technically not, because we live in a world where there's air and there's friction and stuff like that, but you can imagine if we were in space, this would all be uniform circular motion. Now, what I want to do is I want to show you guys this quick video clip. We're going to pause it a couple times and talk about some stuff. And then I'm going to give you guys a little bit of a formative assessment. That was me being official there. We're going to give you guys a little something to work on here. So I can see if you guys remember and understand uniform circular motion stuff. Because again, as testing rapidly approaches, which means we're rapidly approaching a major milestone here. You guys are moving out of becoming freshmen and into being sophomores. Some of you guys will be taking junior classes again. I want to see what you guys understand. I want to make sure you're well prepared. So, let's check this guy out. I can feel the background music too.
In my last lecture to explain today, I want to discuss
Listen to that. That's accent.
emotion.
I do not trust someone with an accent like that.
An example
He sounds like a scientist.
that is spinning some object around your head with a rope. So here I have a gentleman with a rope and there's a ball hanging off the end of it. And what we're going to do is going to simulate what he's doing, and that is he's spinning it around. So as you can see, what we have here is a ball that is spinning around in a circle. Now how would you describe that motion? Well, first of all, the obvious, it's travelling in a circle. But at any particular time, the actual ball is moving in a velocity that is a tangent to that circle. So if I show you the velocity and turn that on, you can see that the velocity at this point is always a tangent to that circle. Now if the ball continues to turn, then you can see that the velocity also changes as a result. Because as you know, velocity is a vector quantity. That is, it has both a size and a direction.
So I'm going to pause this guy
So
here.
although in this example, I'm assuming that the ball is moving around at
Where's my
a
little
constant
cursor
rate,
there?
the size of the velocity.
Oh, so it's on the board. Found it. So, it's always tangent, he said, right? And the velocity is always changing, meaning direction's always changing. Velocity is speed and direction. It's just vector quantity. If it's always tangent, what happens if that string is cut? So he's spinning this ball right here. I cut the string. Where does the ball go?
Nowhere.
Nowhere. She's going to hover there forever?
Oh, it rolls away.
Rolls away or flies away. In what direction? Does it? Does it depend? Let me ask you, sir. Give me perfect timing, sitting right up front. If I cut the string right here, okay, we've got our velocity line. We're looking at uniform circular motion. Which way is the ball going to go? What? Which way is the ball going to go? That way, right? It's going to follow the velocity line. If the ball were, the string were there and I cut it, which way would the ball go? Up, right? It's always going to go at a 90-degree angle, tangentially, close to a 90-degree angle, to the radius, right? It's going to follow that velocity line. We know this. Well, I don't know if you guys have ever seen anybody like use a slingshot or anything like that, like the old-timey David and Goliath style slingshots. No? What? Yeah, I have to record myself teaching. I have to record myself teaching. It's for my evaluation piece, so they can make sure I'm a good physics teacher. And if you want to say something horrible, now's the time. Because Bergman's worst. Don't trust him. He's terrible. But this is the uniform circular motion stuff that we've talked about, right? Which way is the force directed? Which way is my force going? So what forces are acting on this ball? Yeah. What forces are acting on it? Coming in, AJ again. AJ! I'm never for you in a minute. What forces are acting on this ball? Give me one. I'm spinning it around in a circle. Right? It's moving. It's accelerating, so we know it's got a force. Right? It's mass times acceleration. Give me one force that's acting on it. Give me one force. Anything that's moving is feeling what?
Applied
The applied force. Okay. What else?
Where did even start with a wait, I know this is
What do we call when you rub your hands together? What makes them hot?
friction.
Friction. So it's got the friction force pushing this way, right? We've got the applied force. It wants to shoot off in that direction. What keeps it moving in a circle, though? This is you telling me. If I'm spinning something in a circle, what keeps it from flying off in any direction? Well, gravity keeps it going down, right? What? My hand is keeping it going. What's keeping it from just flying off? What's keeping it moving in a circle? Well, the speed is keeping it from just falling down, yeah. But what's keeping my keys from just slingshotting through that door right now? Don't overthink this one. But yeah, what's keeping it moving in the circle? Let's think about it. All right, let's break it down. Keys want to go whichever direction they're moving in, right? So if I let them go at the top, they want to go that way. If I wanted them to suddenly fly off in a direction, what do I have to do? Let go. Right? Let go of what?
I know the word. Hold up. Start with an F, I think, right?
Don't overthink this one. What do I have to let go of? No, of course. What part do I let go of? The string, right? The lanyard piece.
Yo,
Right?
yo.
I'm telling you, don't overthink this. You're like 2 steps ahead of where I want you to be. Right? So the lanyard is holding the keys in place. So the force is coming from the
String.
Force is directed inwards. Our centripetal force is directed inwards, holding it in place. Right? That's what's keeping it from flying off in any direction. They are experiencing friction as well. Gravity, in the case of me swinging them up and down, is pulling them down. Right? My applied force from my arm is what's keeping them moving in the circle and not just falling down. Right? But it's the actual string itself that keeps them from just shooting off in any particular direction. If at any moment that string were to snap, the keys would just go flying. If the force is that way, then it also means the acceleration is inward towards the center. So acceleration in, force in, velocity out. At a 90-degree angle. And I get very confused. Just think about it. The string's keeping them going. If the string snaps, they fly off. Right? Directly in a line from where I let them go. Now, we're going to kind of take a look at this, and I don't want to go through too much more lesson time here. Alright, I want to kind of shift gears. Let's take a look. It's in a book. Reading it now. You guys don't remember reading Rainbow. First of all, it was about books, and you guys don't read books anymore. You guys all have everything electronically now, which is a good thing. It's also on TV. I don't think anybody watches TV. So, do me a favor, sign in Kahoot. Let's see what you guys remember. What you guys still know. What we need to talk about a little bit more. So I'll give you guys like 30 seconds to sign in. 651-4153. That code is 651-4153. Sign in. Let's see what you guys remember. As I record myself teaching for my evaluation piece. They need to know that I'm a good physics teacher. So I act like a good physics teacher when I'm on camera here. Recording myself. It's weird though, recording yourself teaching. Not because I like hear myself talk, because I hear myself talk all day. It's weird looking at the side of your own head. Because I see my front profile. The back of my head looks like the back of anybody else's head. It's just the back of a head. It's head shaped with hair on it.
Especially if it's yours, it's like
Yeah, but seeing the side of my face all the time, it's like a weird angle that you never actually look at. It's very sort of like unsettling. Alright, gentlemen, sign in. Let's see what you know. Michelle's gonna sign in too.
Oh, okay. Wait, for a grade?
Sure. I'll give you a grade. Participation grade. What? Ken has been here yet. He's not here yet. He wasn't been here yet. This is it.
This is it?
Skipping? Well, this is it for now. You've been here this whole time. You should know that.
Yeah, like this is everybody in the whole building in each class. I'm not as local.
Why? It's a nice, easy day
There's
for you.
barely people here, and I went to go home.
It's a nice, easy day.
I still got stuff.
Get to hang out, relax.
Except for only in this class I have class. Next class I got a test and a few other things I need to finish.
Do you want me to give you a test too? Get you in the mood? Get you in the mode for...
No,
We can do a test.
no, thank you.
Alright, what counts as a test grade?
Good.
Wild card.
No, We'll do
Alright.
reverse. You doing the test.
I am. I'm recording myself right now. I'm going to get graded on my ability to teach.
Why do you grade on your own?
I don't grade myself. I get graded by administration.
Like it. Like it. Like
I'm gonna go now.
Good morning, good morning. Do we've ever signed on in perfect timing?
No, it's not leaving wrong.
Two cahoots. Alright. It's Tariq, AJ, and Brad are in. So waiting on 1, 2. Timo and Natalia just got me.
Us.
I like that. Is that like a bearded frog? With like 80 sunglasses on?
I weird. I have these.
He was just jealous because he didn't get here soon enough to get that sweet character.
That's it. It's mom too.
Alright, you ready? 3, 2,
Hey,
1.
Laptop.
We're not sending you, send me a second.
I ain't touched my laptop all weekend. We had homework.
Come on.
Hey, Mr. We have Miss Eward on the paper. The one on the paper. Yesterday, so
Alright, so.
the one on the paper.
Number 1, car moves around a circular path of constant rate at a constant speed, which is true.
Well, I just got my.
The car's velocity is constant, the acceleration is constant, the acceleration is 0, the car's acceleration is directed towards the center.
Mr. B, I'll be
AJ, better
right.
get this one right.
I'll be right back.
You gonna come back with laptop?
Nah.
Come back with... G. Find a way right there.
I clicked the wrong one by accident.
You better get this one right. Because you just gave me like the answer to this one.
I clicked the wrong one by
I
accident.
put the game code and it's not letting me in.
The acceleration is directed towards the center. Did you put a space in it?
I meant to click green by clicking.
6, 5, 1, 4, 1, 5, 3. No, quiz me. No, you're right, website. Oh, snap. So the velocity is constant. We know the velocity can't be constant. Why? Because it's changing direction. Velocity includes direction, so that doesn't make any sense. The car's acceleration is constant, right? No. The car's acceleration is 0. It's not 0 because it has an acceleration, right? The acceleration is directed towards the center. Our force towards the center, our acceleration towards the center. Good morning.
That's why I'm left.
Alrighty.
I clicked the wrong one. I meant to click green.
And an object moves in a circular path at a constant speed. Which of the following is true? Acceleration is not 0 and causes the car to slow down. Acceleration is not 0 and changes the direction of the velocity. Acceleration is not 0 and causes the car to speed up. None of the above. I'll give you a little hint here. Read the question. It's at a constant speed. So that should help you a little bit. So if it's at a constant speed, it's not going to slow down or speed up. Use the question and answer the question. Alright? A good rule of thumb for when you guys are testing and things like that. Use the question to answer the question. Use the test to take the test. So acceleration is not 0 and it changes direction, or none of them. Right? We know acceleration changes velocity. And velocity is displacement over time, right? Displacement has direction. Meaning, if it's changing direction, it's going to accelerate by changing the velocity. Right? And we know that again because if I spin something in a circle, depending on where I let it go, it's going to fly off in different directions. An infinite number of possible directions. Brad's killing it right now.
Shit.
I'm gonna turn over the marker to Brad soon. I'll start kicking back at my desk. Let Brad teach the class. An object moves around a circular path at a constant speed of 5 revolutions in 20 seconds. Find the period. Remember, the period is just how long it takes to do one full revolution. I said that really fast, and I apologize, but I want to make sure I got that out before the question time ended. So again, it's going around 5 times in 20 seconds. How long does it take it to go around one time? 5 seconds, 10 seconds, 4 seconds, or 20 seconds. Again, use the question to answer the question. It's not going to be 20 because it goes 5 in 20. If it can do 5 in 20, 20 divided by 5 equals
I even get to see if you see it.
4 seconds.
Wait, see this?
AJ making moves. Nat making moves. Pivo about to sign in. That come from behind victory. If occupants of a car feel heavier than usual on part of the road, what part are they on? So imagine you're driving down the road, right? Flying down the road in your brand new Ferrari or Lamborghini.
Is that go? You got that, huh?
And suddenly you feel like you're way down in the seat. Right? You feel like you're just...
It was.
What part of the road are they on?
You got it. You got it.
The dip. Right? What? Something in the road. Dips down. Pulls back up.
How is it not a hill?
How is it not the hill? Because as you're at the top of the hill, you're going to feel like you're coming back up. You're going into the dip. You're going up the hill, you're going to feel like you're leaning back. Right? Again, imagine you're in some race car. Accelerating up a hill, you're going to feel pulling down. Think about roller coasters.
Too busy just over that.
That was tricky because I don't think I knew what the dip was.
It's
just the bottom of a hill. When an object experiences uniform circular motion, the direction of the net force is AJ. Get this one right. In the opposite direction of the motion. In the same direction as motion, towards the center, opposite the direction of motion, away from the center.
Spider-Man comes out next month. I'm going to water park. I'm not water park.
4, 3, 2. Can we send in yet?
Bro, I did not want this dumbass.
Towards the center. Force is towards the center. Remember, that's the string holding it in place. The force of the string is keeping my keys from flying off. If we snap the string, the keys go flying. Net force is towards the center. Velocity's outwards. Ooh, look at that.
You've been 14
On the
for like
board.
a year now, bro. Yes, you've been 14 for like a year now, bro.
How old are you? You're 14?
Like,
Kids these days.
You've been 14 now.
When I was your age, I was 15.
Year, bro.
What forces need to move an object in a circle? Weight, kinetic friction, centripetal force, or static friction? Which one's going to move stuff? Which force is needed to move an object?
It's yellow.
Is it? Does that one make sense? Centripetal force. Static friction and kinetic friction, remember, are holding things in place or slowing down their motion. Right? Either I'm moving and I feel friction, or I'm not moving and I gotta overcome the friction to get moving. Weight is just what?
Mass.
And the mass is how much you have. I have a weight because of
Then this.
not density. What's giving me weight? Oh, why do I weight gravity? I say, why do I weigh less on the moon than I do here?
Me either. Because I went to the class and I go, oh, this shit was depressing in there.
Third place. Oh, did that come from behind victory? Alright.
This classroom looks so depressing in there, bro.
An object is a period of 4 seconds. What is the frequency of its motion?
So I just walked back there. I know he here today too, bro.
Mr. Rashid,
It's green.
I think red. It's green.
This is a
It's definitely green. Watch me
I think
go.
it's green.
It's definitely green.
I should probably.
It's probably.
Is it green, or is he trying to throw everybody off by saying green?
I pick green, so.
I think
People.
yellow.
I think it's
Orange.
Or not think red.
It's the purple one.
Oh,
I'm tired of it.
0.25
Stop.
Oh,
it.
white.
is
I like
a
that.
period of
That's a
4
good
seconds.
Yes.
Right.
Star.
I like that.
Boom.
so did I.
You said I started.
You told me to stop. I said you started.
I.
Think his white.
Bro, I told you it was red. It was yellow.
We're gonna give. I'm gonna give you guys. Make sure.
It was
Well, actually,
red.
when you guys are testing, you should have a formula sheet
It
that
was
they give you with the important formulas, like the period on there.
We tested. We.
No, it's
What is the period of the hour hand on a clock?
Oh my God.
Is it 60 seconds? It depends on the time. 1 hour or 12 hours.
Is it? It's blue.
it was.
Depends on the time.
Yeah.
So the period of the hour hand changes.
No.
No, it's every hour. It's every hour.
What is the period?
12 hours.
Oh yeah.
I'm better all these rings.
It's easy. You got it wrong. Chill.
The period
I've been very angry. Oh shit. I had.
12 hours.
Look at you.
Because think about it. How long does it take the clock to go from wherever it is all the way back to where it is? 12 hours, right? From midnight to noon. It can depend on the time if you have a broken clock. Like my watch runs fast sometimes, so that affects it. If I wind it up at like 11 o'clock, it runs differently than if I wind it up at 1. But that's because I have a crummy old bootleg watch. Right? My sweet old 1980s Timex. Takes 12 hours to go from like, let's say noon to noon, 1 to 1, or from midnight to noon, 1 to 1, 2 to 2. The minute hand is a period of 1 hour. What is the period of the minute hand on a clock? Oops. I think I just told you this.
What?
How long does it take the minute hand to go around? Once again, assuming you're not using my crummy clock here.
Well, it has to be 6 seconds.
60 seconds?
I got
1 hour.
What the fuck?
It takes 60 seconds for the second hand to go around one whole time. You kids today with your digital clocks.
Chinese are called that.
I got you with the next answer.
You got this?
Got it.
Alright.
I got so much shit.
People are going to have some competition for BJ's going for that first place spot. What is the period of the second hand on a clock?
Oh, we got a coupon on
Isn't it the same question as that?
I thought
That was the minute hand. This is the second hand.
Don't got it.
Are you talking about the red one?
Yeah, the little one.
Wait, you talking
So-
about the little red one?
Yeah.
60 seconds?
That's the second hand. Is that how long it takes you to go around?
Got a coupon on it.
60 seconds!
Yeah.
Right, again, for those guys who are never using a digital clock, it's the little quick one. Sometimes it's usually red on like old-timey school clocks. But it's the one that moves faster. It's got to go 60 seconds in one circle to move the minute hand. One, it takes 60 minutes for the minute hand to go around. To move the hour, 1, it takes 12 hours for the hour hand to go around. All questions you may see coming up in 10.
I'm not staying home this weekend. Obviously, you'll stay home this weekend. I'm gonna stay home this weekend, right?
An object rotates in a period of 10 seconds. How many revolutions will it make in 25 seconds?
Yeah, I know.
So this is the last really, really tricky one. An object rotates in a period of 10 seconds.
I'm looking at my
Kiba.
It's 5 seconds, right?
You're in like second place right now.
It's I'm not getting to your book right there. What did you
So 10 seconds. Go in a circle.
Nah, it's 5, right?
Because I forgot to.
How many will make it in 25?
2.
2.5. So think about it this way,
Take it out, man.
right? Think about it logically. If it goes around one time in 10 seconds, in another 10 seconds it'll go around 2 times, right? And then in 5 more seconds it'll go 2.5. Or 25 divided by 10 is 2.5.
Did you look at?
If it takes me 10 minutes to walk to school, right? I can walk to school. I can walk back to home. Then I get halfway to school again. 25 minutes.
Mister, do you have some scissors?
Do I have scissors?
Yeah.
Why?
So I can cut this. Cause I don't know how this happened. Like, how does this even
Before
not
you cut that,
Yes, it is, bro. 'Cause I don't know how this shit happened.
alrighty.